In this lecture, I shall introduce you the major historical developments in the field of operating system. We shall learn how operating systems have evolved from the rudimentary set of libraries to the present day sophisticated GUI-based software. Advancement in computing technology has always been affecting the operating system design goals and objectives. Internally, operating systems vary greatly in their functionality and services as they were built to cater different computational needs and user expectations. The operating system development milestones include batch systems, multi-programmed systems, time-sharing systems, and real-time systems. The objectives of this lesson are to explain you how operating systems evolved to meet the requirements of underlying computer systems, and to discuss the operating system design goals that were affected by developments in computing platform. Batch systems. In 1960s, the common form of the computation was mainframe computer systems. Computing was expensive at that time, and only big organizations were using computers. Individuals could use the facility in designated computer centers with the help of an operator. Users used to give set of punch cards to operator of the facility for the execution of their programs. These punched cards contained program instructions as well as data. One special card, the header card, carried the control information such as which compiler to use. Operators used to group the similar jobs from different users and run this batch, hence known as batch systems. Job similarity was decided based on the needs of resources or the other criteria such as length of the job. Jobs are executed in the order of their arrangement in the batch. At the end of the day, user returned to the operator for the collection of the program execution results. One of the major limitations of batch systems was the underutilization of resources, because at any given time only one job was in the memory using the resources. However, a single job cannot always keep the CPU busy. For example, if job invokes some IO operation, then CPU goes idle until the completion of the IO request. Batch operating systems didn't do much. They just served as control transfer program, passing the execution control from one job to the other job upon the termination of the current job. Multiprogramming systems. It was the era of mini computer when operating systems took a leap forward. Concept of multi-programmed systems emerged to resolve the single job problem of batch systems. The idea was simple: keep several jobs in the memory, so if one job stops executing due to IO wait, pick the next job from memory for execution. On the contrary to batch systems, where memory holds only one job at any given time, multi-programmed systems keep several jobs in memory. These jobs are waiting the allocation of CPU to start their execution. The rest of the jobs are kept at disk in a special area called job pool. The decision that which job has to be moved from job pool to the memory is made by special function of the operating system known as job scheduler. The other major operating system advancements included memory management and protection. As several jobs are kept in the memory, so memory management service was the part of operating system to take care of the issue such as memory allocation, memory deallocation, keeping track of the occupied memory space as well as free areas of the memory. Operating system also provided protection mechanisms to ensure that processes don't interfere in each other's address space. Moreover, interrupt handling support was provided in the operating system. Although multiprogramming did lead to enhanced throughput of the system, the systems still essentially operated in batch processing mode and lacked user interaction with the program. This figure gives a glimpse of the working of multi-programmed system. In multi-programmed system, main memory holds several ready-to-run processes. As you can see, process P2, P3 and P4 are waiting of their turn for execution, while process P1 is in execution state. Remember, the set of processes in main memory is the subset of processes placed in job pool, waiting the memory allocation. During execution, process P1 made an IO request. For example, it wants to read data from a file stored on secondary storage device. Having issued data read request, this process cannot execute any further until the needed data becomes available. Hence, this process must wait for the requested data. It is going to take considerable time to read data from disk. As being mechanical in nature, disk is much slower than the processor. So instead of wasting the processor cycles, operating system will move this process from processor to memory and start executing the next ready to run process in the memory, which is the process P2 in this case. Even if processor at some point understands that P2 goes into the waiting state, then P2 will also be moved out of the CPU and process P3 will be allocated CPU. Hence, we can observe from this example that CPU never sits idle until it has jobs available to execute. Time-sharing systems. A logical extension of multiprogramming is time-sharing or multitasking system. A time-sharing system provides an environment in which several users can run multiple processes in interactive manner. The idea is memory holds a collection of processes belonging to different users. A process is selected to run for a certain time period. This time period is known as time slice or time quantum, and it is usually 10 to 100 milliseconds in length. Execution control is switched from one process to the other process either upon the expiry of the time slice of that process or when the process goes for IO waiting. These switches occur so frequently from process to process that user can interact with their programs while they are running. As the system switches rapidly from one user to the next, each user is given the impression that the entire computer system is dedicated to his use, even though it is being shared among many users. The important OS considerations for time-sharing system include virtual memory. Virtual memory is a type of special memory that is allocated on the disk for the usage of main memory. Virtual memory may also require the support of disk management, as the memory is created on the disk, so system must provide disk management mechanisms as well. Moreover, operating system should provide concurrency control, as many different processes are being run concurrently in the time sharing system. So concurrency control is a must so that these processes could run in a concurrent manner. Moreover, to ensure orderly execution, the system must provide provision for job synchronization. As shown in this figure, section of the secondary storage space reserved for the use of main memory is called virtual memory. Virtual memory enables the execution of programs larger than the size of main memory. Without virtual memory, such programs cannot be executed. These programs are broken into multiple parts, and only those parts that are currently needed for execution are stored in the main memory, while remaining parts are stored in the virtual memory. As you can see, process P1 is divided into two parts, part 1 and part 2. Part 1 is in main memory, while the other part is in virtual memory. When part 1 completes its execution, it would be swapped out to the virtual memory, whereas part 2 would be swapped in main memory for execution. Another benefit of the virtual memory is that processes who are suspended due to some I/O wait can be swapped to make room for new incoming processes. Such processes who are suspended, they can be swapped out to the virtual memory, and thus we can make room in the memory for other processes. In 1980s, computers became affordable for individuals, hence called personal computers. Personal computers gave rise to the GUI-based operating systems. For the convenience of users, menus, icons, drag and drop features, and use of pointing devices have become the norm in PC era. The birth of Internet and client-server architecture has made it necessary to include the networking support in operating systems. Now, operating systems are shipped with protocols like TCP and IP. To get more processing power, parallel computing has emerged, which demands better concurrency control and synchronization mechanisms in operating systems. Moreover, to cater the needs of distributing computing, operating systems ensure transparency, fault tolerance, and communication and coordination protocols. Moreover, widespread use of some softwares such as web browsers and text editors has urged many operating system designers to bundle these applications with operating system. A real-time system has well-defined and fixed time constraints. The system must produce output within the specified time. Such systems are typically used in control applications, which perform some dedicated function. Examples of such systems include scientific experiments, industrial control systems, and medical imaging systems. If a real-time system doesn't respond according to the time constraints, it may fail. For instance, a boiler control system that reads the boiler temperature, and if reading is more than the threshold value, then it raises the alarm. If such a system doesn't perform the operation within the specified time, then system may fail. The boiler may burst and cause damage. Real-time systems may be classified into two types: hard real-time systems and soft real-time systems. Hard real-time systems place the rigid time requirements on the completion of needed operations. The failure of any component of the system means the failure of the whole system. Whereas soft real-time systems don't place rigid time requirements. In soft real-time systems, if operation is not completed within the specified time limit, then it may degrade the performance of the system but won't fail the system as a whole. The design considerations for real-time systems include that typically user interaction is not present in these systems. There are no I/O devices like keyboard or the display monitor or mouse, etc. Users interact with these systems with the help of sensors and actuators. Input is read through the sensors and output is generated on the actuators, such as a camera may read the observations or may read the environment. It can be used as an input device, whereas the robotic arm that might be used as the output device. Similarly, as I gave you the example of the boiler, in that case the output is given in the form of raising an alarm. Moreover, in these operating systems, there is no hard disk drive or the secondary storage device. Rather, instructions and data, they are stored in read-only memory.